And of course, in unitary theories, the representations we discuss should be unitary representations of the symmetry algebra. So there are two natural questions that one can ask. The first one is when an algebra A can even arise as a physical symmetry algebra. And a related question is which representations of that symmetry algebra can actually occur in physical systems. And we will examine two examples, two instances of these questions. Both of them will involve supersymmetric quantum field theories. In the first case, the symmetry algebra will be the superconformal algebra, and R will be the algebra of local operators. And in the second case, the symmetry algebra will simply be the extended Poincare supersymmetry algebra in flat space, and R will consist of particles or strings. So in quantum field theory, we expect the generators Q of continuous symmetries to arise from local currents, J of x. And just like all other well-defined local operators, they should reside in a multiplet script J of the symmetry algebra. So script J is a multiplet of the algebra, and it contains the currents J of x, and those integrate to the charges Q. So in this talk, I will use the old-fashioned notion of current algebra, meaning the action of the symmetry charges on the operators in the current multiplet script J, including the actions of the Q's on the local currents J of x. And if you take this relation and integrate over x, you just get a product of two Q's, and you must reproduce the algebra of charges. So this requirement is actually a non-trivial constraint on both the multiplet J and the algebra itself. So it can happen that some representations of the algebra may actually be inconsistent with the existence of local currents. And a classic example of that is the Weinberg-Witten theorem. In that case, A is simply the Poincare algebra, and the corresponding current is the stress tensor. And it's well known that there are massless single particle representations of the Poincare algebra for any half-integral helicity, H. But if you look at the matrix element, this matrix element of the stress tensor between two states of helicity H for some momentum transfer Q through the stress tensor, then this matrix element is only non-zero if the helicity is bounded in magnitude by 1. And that's essentially because the stress tensor has spin 2, and you can go to a frame when the momenta are back-to-back, so that the net helicity flip is actually 2H. So 2H has to be bounded by 2. And however, if you examine the forward limit of this matrix element, then you're essentially probing the massless particle with a very soft fictitious graviton, so you're just measuring its energy, and therefore this forward limit must both be infrared finite and give a non-zero answer, which is the energy of the particle. So we know that this matrix element has to be non-zero, and therefore the Weinberg-Witten bound holds. Now if one applies the Weinberg-Witten bound to massless single particle representations of the Poincare supersymmetry algebra in diverse dimensions, QQ is proportional to P, then they violate that bound in certain situations. So if you're in more than 4 space-time dimensions, 4 or more space-time dimensions, then the bound is violated when the total number of supercharges is bigger than 16. And this leads to the standard lore that quantum field theories require 16 or less supercharges. Now, there are two caveats to that lore. The first caveat is that the argument doesn't hold in 3 dimensions because there is actually no notion of helicity for massless particles in 3 dimensions. For instance, you can imagine an n equals 9 free massless hypermultiplet. It just has 16 free bosons, phi with an index I, and 16 free fermions, psi, also with an index I. The i's run from 1 to 16, and they're simply spinors of the SO9R symmetry. So this multiplet actually exists. And the other more embarrassing problem is that this argument does not rule out interacting superconformal theories with more than 16 supercharges, which is something that we would like to do, or test perhaps. So in the context of superconformal theories, the notation of the previous discussion would be that the symmetry algebra A is just the superconformal algebra, and the algebraically consistent superconformal algebras have been classified. That's a famous work due to Nahm. And they're very restricted. I list them here in more than 3 space-time dimensions, and this is the list. So the first important aspect is that there are no superconformal algebras in 7 or more dimensions. And the main takeaway message from this list here in 3, 4, 5, and 6 dimensions is that with the exception of 5D, there are always infinite families of possible superconformal algebras for any n, where n is the usual n that labels the amount of supersymmetry. So 5D is an exceptional case. As you can see, it's an exceptional superalgebra that sits here. And already algebraically, we know that only n equals 1 superconformal theories exist in that space-time dimension. And in 60, the structure of the superconformal algebra forces you to discuss chiral supersymmetry, n, 0 supersymmetry. But as I said, there are these 3 infinite families. Now it turns out that not all of these superconformal algebras on the list actually admit a consistent current algebra interpretation. So in this case, the required current multiplet, I'll denote it by script T, contains an R-symmetry current, R, with some R-symmetry indices, that integrates to the R charges if they're present. There must be a traceless supersymmetry current S that also carries some R-symmetry representation, and that integrates to both the Poincare and the superconformal supercharges. And of course, there has to be a traceless stress tensor that integrates to all the bosonic generators of the conformal group. And the commutation relations of the superconformal algebra imply some constraints on the actions of the Qs on these currents. So for example, the action of the supercharge on the R current has to be proportional to the supersymmetry current, because when you integrate that relation, you have to get the correct commutator between Q and the R charge. And similar statements hold for some other of the some other currents, and the last one here that says that the action of the supercharges on the stress tensor is proportional to 0 really means that you only have total derivatives on the right-hand side, so that when you integrate that relation, you get the statement that the supercharge commutes with translations. And of course, as we said before, this multiplet T must be a unitary multiplet of the superconformal algebra. So as part of these papers that I mentioned in the beginning, we have developed a uniform procedure to tabulate the full operator content of any superconformal multiplet in any dimension and for any n, building on the work of a lot of people, but especially that of Dolan and Osborne. And in particular, as an example, we analyzed explicitly all multiplets that contain conserved currents. There's a pretty restricted list. And the upshot of that analysis is that if the current multiplet exists, it is essentially unique, modulo some small caveats, and it has a single bottom component, which is the lowest weight state. But there are situations in which no candidate stress tensor multiplet that satisfies these constraints up here in star actually exists. And this happens in 4 and in 6 dimensions if the total number of supercharges is bigger than 16. So this result pertaining to 60 theories was mentioned this morning in the talk by Vapa. And in 3 dimensions, it turns out that a stress tensor multiplet always exists for any n. But if n is bigger than or equal to 9, again corresponding to having more than 16 supercharges, then T always contains higher spin currents in addition to these currents. And then we know from the work of these gentlemen that the theory should be free, at least locally. So that's consistent with our free hypermultiplet example from before. The machinery that was mentioned there also allows us to classify all possible supersymmetric deformations of superconformal theories by local operators. And this has many applications, including universal constraints on supersymmetric RG flows. And an example that I want to mention that will be useful to keep in mind later in the talk is the case of 4Dn equals to 2 theories. That case was also independently analyzed by Argyris and collaborators. So at the conformal point, there's an SU2R and a U1R symmetry, and the supercharges are doublets under SU2 and also carry U1R charge. And it turns out that there are only 2 kinds of Lorentz invariant relevant or marginal deformations that preserve supersymmetry. The first kind is associated to a flavor current, which resides in a real multiplet Jij with this index structure that satisfies the following shortening condition. And its dimension is fixed to be 2 by unitarity, and the flavor current itself sits at level 2. And then if you hit Jij with 2 Qs contracted in this way, you make a deformation that preserves supersymmetry. It preserves the SU2R symmetry because all the indices are contracted here, but it always breaks the U1R. And the other class of supersymmetric operator deformations are related to chiral operators. These are annihilated by all the Q bars, and the dimension is fixed in terms of the U1R charge. And there, the deformation is given by hitting O with 4 Qs, again with all the indices contracted. So this preserves supersymmetry, the SU2R symmetry, but again, it typically breaks U1R. So the upshot of that discussion is that all deformed superconformal theories, at least, have an SU2R symmetry, but generically not the U1R that was present at the conformal point. And in fact, the same conclusion applies if you deform the superconformal theory by gauging a subgroup of its flavor symmetry. And if the n equals 2 theory has a Coulomb branch, as is the case in essentially all examples that we study, then the SU2R symmetry must be unbroken there, because the vector multiplet scalars are not charged under it. So this allows me to transition into the second part of my talk, which will be about non-conformal n equals to 2 theories in 4 dimensions. And now the symmetry algebra that survives is simply going to be the Poincare supersymmetry algebra and also the SU2R symmetry from the previous slide. And it's well known that this algebra can be extended by p-form charges that are carried by p-brane excitations. So the commutator of q with q bar doesn't just contain the momentum, it also contains a vector charge x. And the commutator of q with q doesn't just contain the ordinary scalar central charge z, but also a two-form central charge y that carries some R-symmetry indices. And here we have the statement that the q's are doublet under the SU2R symmetry. And the charged states are strings for this one-form charge x, domain walls for the two-form charge y, and point particles for z. And of course, it is a standard result that unitarity with this hermiticity condition imposed on the q's implies a BPS bound for the mass, or more precisely the tension of these objects. So the string mass, the string tension is bounded from below by the norm of x, suitably interpreted. You need to look at some particular components of x. Similarly, the mass of a domain wall is bounded from below by the absolute value of y, and the mass of a point particle is bounded from below by the absolute value of z. And when these bounds are saturated, we can get BPS strings, domain walls, or particles. And the question I would like to discuss for the rest of the talk is which of these excitations can actually arise in n equals to 2 theories, and what can we say about their quantum numbers. And again, a major player in the discussion will be the stress tensor multiplet. It still serves as the current multiplet of the Poincare supersymmetry algebra. And as before, all charges in the algebra must have antecedents that are current. So there's the SU2R current here, the supersymmetry current, the stress tensor, and then there are 3 brane currents, 2-form, 3-form, and 1-form that integrate to the charges on the right-hand side that we discussed in the context of branes. And now the stress tensor and the supersymmetry current are not necessarily traceless because we're no longer at the conformal point. And just like in the superconformal case, some of the commutators of the supercharges with the currents are constrained by the form of the charge algebra, because when you integrate, you have to recover the charge algebra. Now I would like to mention some important qualitative differences with the superconformal case. First, the symmetry algebra itself may admit several distinct representations that satisfy these two constraints. So there could just be different stress tensor multiplets, structurally different stress tensor multiplets. And the second statement is that even a single given theory that you would like to analyze may simultaneously possess 2 or more such multiplets. So if you have, say, 2 such multiplets, T and T prime, then the stress tensors and the supercurrents that live inside them may differ by improvement terms, so total derivatives. But the other currents in T and T prime need actually not differ by improvements. And an example that would be very important shortly is that the SU2R current can actually mix with an SU2 flavor current. So a complete list of all possible n equals 2 stress tensor multiplet is not known, but we know many examples, and we would like to understand if there's in some sense a preferred multiplet that we should discuss. And to some extent that's true. So it turns out that nearly all non-conformal n equals to 2 theories that we know and understand that have an SU2R symmetry seem to admit a stress tensor multiplet T of a certain kind that was originally introduced by Sonius a long time ago. And this multiplet is built on a real scalar T, which is the bottom component, and then it satisfies the following set of shortening conditions. When you hit it with 2 Q's contracted in this way, then you get a complex operator Zij that itself satisfies the shortening condition of a conserved current multiplet. And indeed, this is nothing but the complex flavor current that contains the central charge current Z mu. And when Z vanishes, this collapses to the superconformal multiplet. Another way to think of this multiplet is that's an n equals 2 version of the n equals 1 supercurrent that was discussed by Ferrara and Zumino. Now here's some of the operators, or actually all of the operators in the Sohnius multiplet in more detail. We've already mentioned T and Z and these currents here. There are two operators here at level 2, a 2-form W and a 1-form R. These are generically not conserved currents, except when you're in a superconformal theory where this becomes the U1R current. And then you see that at level 4, at the top level, there's the stress tensor, the central charge current, and also a complex scalar. So one immediately sees that among this operator content, there are no genuine brane currents of the form that we parameterized by x and y before. And then one concludes that since there are no brane currents, there can be no charged objects. And therefore, there cannot be BPS strings or domain walls in theories that have this type of current multiplet. And this is consistent with some n equals 1 result that I obtained a few years back with Seiberg. There we argued that BPS strings cannot arise in theories that have a Ferrara-Zumino multiplet, and BPS domain walls cannot arise in theories with an R symmetry. And here we have both constraints present, so neither of them can arise in these n equals to 2 theories. So the only excitation that we have left to discuss are the BPS particles. And these are typically studied on the Coulomb branch, where, as I said, the SU2R symmetry is unbroken. So in order to understand that a bit better, we should look at the commutator of Q with the supersymmetry current that should give some current that integrates to the central charge. But that not only includes the contribution from the central charge current Z mu, but also a total derivative of this 2-form W, which at low energies is just given by the electromagnetic field strength. And that's responsible for the boundary contribution that gives rise to the electric and magnetic charges in the central charge formula. And for the purposes of this talk, it will suffice for me to take a single vacuum and a single charge sector. So I'll fix all these sectors. And then Z is just a complex number that I can easily rotate by redefining some phases to just lie along the real axis. And if I've done that, then I will say that particles are the ones with positive Z, and antiparticles have negative Z. And as always, I will analyze these particles by going to the rest frame, where the bosonic little group consists of SU2J of spatial rotations and the SU2R symmetry. And for the purposes of discussing these particles and the BPS bound, it's useful to introduce these linear combinations A plus minus of Q and Q bar. A plus minus is a doublet under both SU2Js, and it satisfies these hermiticity conditions. And its commutators are easily obtained from the SUSY algebra. A plus and A minus anti-commute. And among themselves, they just essentially anti-commute to the identity with a coefficient Z plus or minus M. Okay, so BPS particles are the ones that satisfy M equals to Z, and for those, A minus vanishes. This leads to a multiplet that has 4 states in what's called a half hypermultiplet. So there's a spin-up component of a fermion with no R charge. Then you act with some raising generators, which are the A pluses, and you get the 2 R symmetry doublet states of the complex boson. And finally, when you raise again, you get the spin-down state of the fermion. And anti-BPS particles are very similar. They have M equals to minus Z, and the roles of A plus and A minus are interchanged. And finally, if the multiplet satisfies this inequality, then it's long, none of the A's vanish, and you get a multiplet with 16 states. So this is not, in fact, the most general BPS representation that you could discuss. More generally, we could tensor the half hypermultiplet with an arbitrary representation of spin J and spin R of the little group. So the J is the Lorentz label, and R is the SU2R label. And that just means tacking on to all the states in the half hypermultiplet extra labels M and S that keep track of the weights under the little group. Now, multiplets with J not equal to 0 actually occur. They're very common. For example, if you take J equals to a half, and R equals to 0, then you get a representation that corresponds to a massive W boson. But empirically, it was observed in many examples that multiplets with non-zero R do not seem to occur in quantum field theory. And this was formulated in the no exotics conjecture of Gayotto, Moore, and Knightsky. And it's called no exotics because putative multiplets with R non-zero were called exotics by these authors. And there was some further work on this conjecture by these authors. And I would like to mention a few consequences of the conjecture. First of all, it implies that long multiplets cannot actually come down and hit the BPS bound and fragment into a bunch of short multiplets. because one of the decay fragments would necessarily have to be exotic. And an immediate consequence of this is that protected indices, which count BPS states with signs, actually coincide with the physical degeneracies of the states. So it makes these indices more physical. And mathematically, it turns out that the no-exotics conjecture implies interesting constraints on the cohomology of moduli spaces that arise in counting BPS states that was explored in a lot of detail by these authors. Now, as I already alluded to earlier, in the presence of an SU2 flavor symmetry, the SU2R symmetry is ambiguous. You can define a different SU2R tilde symmetry that's simply the diagonal subgroup of the original SU2R and the SU2 flavor. So that's just as good. And a simple example to keep in mind is just a massless hypermultiplet with scalars Qi and fermions psi. And here I is an R symmetry index under the original R symmetry, and A is a flavor index that sits both on the scalar and on the fermion. And if you do the mixing, it means that you replace all of these doublet indices by doublet indices of the tilde R symmetry. And then it's obvious that the fermion acquires a doublet index under the SU2R tilde. So according to the previous definition, this multiplet is exotic with respect to the SU2R tilde symmetry. So what this simple example tells us is that the statement of the no-exotics conjecture is ambiguous in the presence of this SU2 flavor symmetry. And what we would like to do is to state the conjecture with respect to the original R symmetry, the standard one that we intuitively always think of. But it's not a priori clear how to abstractly distinguish the two SU2Rs in a model-independent way. So again, the currents come to our rescue. Turns out that while the two R symmetries are indistinguishable at the level of charges, they in fact arise from two completely different current algebras. So the R current that gives rise to the original R symmetry resides in the Sohnius multiplet that we discussed. And the R tilde current that gives rise to the mixed R symmetry sits in a completely different, much less familiar multiplet. So the goal for the remainder of the talk would be to outline a proof of the no-exotics conjecture with respect to the SU2R current in the Sohnius multiplet. And to that end, we will examine its forward matrix elements between BPS states, where it simply measures the R charges. And for now, we assume that all forward limits exist, postponing a small subtlety to the next slide. So the argument will be by contradiction. We will examine this matrix element of the lowering component, R22, of the current between the fermionic states of the BPS states with arbitrary labels S and S prime for the R symmetry. And I've suppressed the spin indices because they will play no role. And if the R symmetry representation of the BPS state is non-zero, so if it is exotic, then we can in fact choose S and S prime to differ by 1 unit like this to get a non-zero matrix element here that simply captures the non-zero matrix element of the lowering operator, R22. But in fact, I claim that this matrix element actually has to vanish, and that will establish the no-exotics conjecture. So in the Sohnius multiplet, you can write this component of the R current as 2 Qs hitting the bottom component, and because it's acting on BPS states, this combination of supercharges has to vanish. So we can move the supercharges around and derive a Ward identity relating these two matrix elements. That's the matrix element we started with. This is the matrix element of the bottom component T between the two scalar states in the BPS multiplet. And there are many such Ward identities that you can derive, but none of them are sufficient to show that the matrix element vanishes. So the extra ingredient we need in order to finish the proof is the CPT symmetry of relativistic field theory. And since CPT, which I'll call theta here, squares to -1 to the f, you can just look at the SUSY algebra and immediately infer that up to a sign which is convention dependent, the supercharges and the central charge have to flip like this under CPT. And you see that there's some interesting signs and phases in these transformations, which are forced on you. And this also immediately fixes the theta transformation of all Sohnius multiplet operators, because some of them integrate to the charges. So the last step in the argument will be to chase our Ward identity through a commutative diagram that involves acting with CPT on both sides. So this was the original Ward identity we derived in the BPS state. Now we're going to act with CPT. If we do it here, CPT flips the lowering operator into the raising operator, and then we simply get the matrix element of the raising component of the current between the BPS, the CPT transformed BPS state. So this is the CPT transformed BPS state with the superscript theta, and it's an anti-BPS state. So you get this matrix element with a coefficient plus. If you go around the other way, you start with this matrix element, then you use the fact that CPT does not affect the bottom component, T, to simply relate the matrix elements of T in the original state and in the CPT conjugate anti-BPS state. Okay. And now, to repeat the first step, you derive a ward identity using the supercharges that vanish in the anti-BPS multiplet to relate this matrix element to this matrix element. But in the anti-BPS multiplet, a different set of supercharges vanishes than in the original BPS multiplet, and therefore there are some small differences, and there's a crucial sign. So you end up proving that this matrix element is equal to minus itself, and therefore it vanishes, and so does every other matrix element on this diagram. So we proved that the matrix elements vanish, and therefore the no exotics conjecture follows. The small subtlety I alluded to on the previous slide is the fact that the matrix elements of T actually diverge in the forward limit. And this is due to soft single photon exchange. Now this is a deep IR effect. It's weakly coupled. It can be computed exactly and universally and just subtracted. And this simply has the effect of redefining what we meant by Z in the Sohnius multiplet to some Z effective that actually satisfies the same supersymmetry condition. And this simply has the effect of transmuting the UV central charge current into the IR central charge current that also picks up the contribution from electromagnetic charges. So this leads me to conclude the general lesson of the talk, which is of course not new, is that in quantum field theory, current algebra can exclude phenomena that are allowed at the level of the charge algebra. And we saw that in two examples. We excluded superconformal theories with more than 16 supercharges in 3 or more dimensions. And in 3 dimensions, we were only able to exclude interacting superconformal theories. And we excluded exotic BPS states in 4D n equals to 2 theories, establishing a conjecture of GMN. Now, 2 points I want to mention quickly is that this argument against exotics did not require a UV complete theory. So for example, you could consider a 5D n equals to 1 theory that also has a Sohnius multiplet and compactify it on S1. And then some of the 4D BPS states in that compactification come from strings wrapping the S1, BPS strings. And applying the no exotic statement to them shows that those strings also do not carry R charge. And finally, the entire discussion can be repeated for BPS particles in 5D and then uplifted to a statement about BPS strings in 6D. And similarly, there is a 3D version, which is a bit richer because in 3D n equals to 4 theories, there are 2 SU2R symmetries rather than just 1. And finally, it would be very interesting to extend the argument we gave to frame BPS states which are bound to a defect. So I'll end here. Thank you.
Any questions? If you suppose you were to allow to break SU2R, in that case we know that there are BPS strings.
For example, if you add an FI term.
Yes.
Yes.
But what about BPS domain ones?
I think I gave an argument excluding them.
But you only discussed theories that have SU2R symmetry.
Oh, well, okay. More generally, any theory that has an n equals to 1 FZ multiplet. Sorry, an n equals to 1 R symmetry. So if you still preserve a U1 R symmetry, yeah, it will also be excluded. If you preserve none, I'm not sure.
Yes. So are there any examples with BPS domain ones in n equals to?
I do not know any, but for sure we would have to study a theory without any R symmetry.
Yeah, that's obvious.
But it's clearly not enough to just turn on a single FI term. At the very least, for example, you would have to turn on 2 or something.
Yes.
Yeah.
As far as I know, I don't know of any example where there are BPS domain laws, even without R symmetries.
Yeah, I don't know them either.
So maybe it's just impossible.
That's conceivable.
Any other questions?
Over there?
Oh, yes, please.
Yeah, so can you comment if there are some consequences for the superconformal index? So play has some formalism related.
Well, there's a conjecture relating the BPS states to a limit of the index.
Yeah.
And since we can prove the constraint on the BPS states, it's natural to think that there should be some constraint on the index, but I don't know what it is, since the relation is, first of all, not well established, and secondly, very complicated. So I think one needs to understand it better before we can explore the consequences of this constraint. Yeah.
Not clear on this ambiguity with mixing the SU2 symmetry. If you want, you can always pick another basis. But with SU2, if you pick something that is a linear combination, then you no longer have the SU2 times SU2 symmetry.
Well, it's not the continuous ambiguity that you have in the n equals 1 case, but you can, if you have two of them, then you can look at the diagonal subgroup.
Right, but then you lose one.
Absolutely, that's fine.
So there is a preferred basis where you see the full SU2 times SU2.
Right, I agree with that.
And I assume this is the basis you use.
But this mixing doesn't destroy the symmetry. It just makes it hard to see them.
Right, but there's a preferred multiplet, the multiplet where you see two multiplets.
Yes, exactly. The multiplet where you mix the two is just one much bigger multiplet where you fuse the two currents.
The preferred one is the
Absolutely.
irreducible.
Absolutely, yeah.
Okay, due to time limitation, if you have any more questions, please ask in private. Let's thank Thomas again.
Thank you.